So artificial general intelligence is a topic of great interest. So the first question that we face, right, is what is artificial general intelligence? And so just a rough gloss is that artificial intelligence is artificial intelligence or AI that is equal to or surpasses human level intelligence. AGI is often contrasted with narrow AI, so which may surpass humans, but only at a narrow task, such as playing chess or something like that. And the development of AGI is of interest because it's been a kind of central organizing North Star goal of research into AI for a very long time. And though narrow AI has been with us for a long time, recently technological advances in machine learning suggest to many people that AGI may be with us already or may be emergent in the next 10 years or something like that. So, for example, some think that large language models such as ChatGPT or Gemini show sparks of AGI. So there was this landmark paper by a team from Microsoft claiming that ChatGPT already showed sparks of AGI. And one of the other reasons we're interested in artificial general intelligence is because it seems to hold out the hope of both great benefit to humanity and the risk of great harm. So, for example, with regard to benefits, people hope, I mean, this is one of the things that's behind the OpenAI charter. People hope that AGI will lead to, solving the world's problems, advancing the progress of science, finding the cure for cancer and so forth. So there's great benefits that are hoped for, but there's also great risks. So many people worry that a race of artificial super intelligent beings will emerge that will outcompete humans and render us extinct. Maybe some people might welcome that outcome, but at least some people are concerned about it. Okay, but the problem is there's very little consensus on what AGI actually is. So here's a quote from a recent survey by Morris and colleagues from Google DeepMind. If you were to ask 100 AI experts to define what they mean by AGI, you would likely get 100 related but different definitions. So what are we supposed to do in the face of this kind of conceptual abundance? So one suggestion that's put forward by Laird and colleagues is that what we need to do under these circumstances is first provide a crisp definition of the concept of AGI, and then specify how to test for AGI. And I have to say, though, as a philosopher, I really like this call for a crisp definition. It's appealingly rigorous, but it seems to me that, if anything that we've learned from like 20th century philosophy is that crisp definitions of most interesting terms are not possible. So I think we should set our sights a little bit lower. Okay, so no crisp definitions, but we can give something like a gloss, and maybe we can give some necessary conditions, so requirements for AGI. Okay, but what do we do about the conceptual abundance, right? How do we decide which concepts to choose? And I want to suggest that we need to engage in some kind of conceptual engineering or conceptual ethics. There's not one concept of AGI out there that has a special glow. We need to decide which concept of AGI works for us, which one captures the things in AGI that we care about, both from a theoretical perspective and from a practical perspective when we're considering risks. Okay, so to do that, we need to ask why AGI matters, and that's what I'm going to do in the first part of the paper, and then try to give a gloss on some of the things that we care about in AGI, a kind of gloss on the concept that we, I think, at least for some purposes, should choose. And the next step is to determine how we could test for that thing. And there's a sort of well-known difference between two ways of testing for cognitive capacities in artificial systems, what might be called shallow and deep methods of benchmarking. So the shallow methods were started off by Alan Turing and the well-known Turing test, which basically just looks at a system's behavior. So basically the shallow methods are looking at a system's behavior, its performance on various tasks. And Turing, for example, famously suggested that we should replace this question, can a machine think, with the question, can a machine pass what he calls or play the imitation game, which has now been now called the Turing test, right? So his thought was that instead of asking the question, can a machine think, you should ask the question whether the machine can hold its own in a conversation with a human long enough to fool the human judge into thinking it's human. So this is one of the kind of standard cases of the shallow test of shallow benchmarks of intelligence. And there are many tests that are carried out that are similarly, even today, people don't use the Turing test. There are some funny articles about how ChatGPT broke the Turing test and so forth. In some sense, ChatGPT has definitely passed the Turing test in some sense, because people have in fact thought it was intelligent or a human. But I think, sorry. Many of the benchmarks that are used, the more serious benchmarks that are used are behavioral. Okay, so the pushback comes from people like Ned Block and John Searle, who argue that in slightly different ways, who've argued that behavioral information is insufficient to tell us whether a system is intelligent, basically because intelligent behavior can be produced by an unintelligent system. And so to determine whether a system is intelligent on the kind of deep approach, you have to look under the hood at its cognitive architecture. You have to see what kinds of representations it is capable of understanding or grasping, and you have to see how it processes those representations. Okay, so I'm going to argue for a deep approach, as the title of the paper suggests. Okay, so let's start thinking about how to choose a concept of AGI. So to begin with, I think it's worth just bearing in mind that research into AGI is just unabashedly anthropocentric. So since the 1950s, when it was begun, one of the major lines of research into AGI was to produce a system that whose intelligence was in some sense indexed to human level intelligence. I mean, the rough gloss I gave has to do with a general intelligence that is like, in some sense, or surpasses human intelligence. So one kind of aim that was a theoretical aim of research into AI was to actually model human cognition in detail. So there's a sort of strand of AI research that just seeks to understand the human mind by producing artificial models of it. But the kind that's sort of interest to me here, and I think that's of interest in current speculations about risks and current hopes about benefits, is this kind of second sort, which is the aim of creating AI systems that emulate human intelligence in some important respects, but without the limitations, right? So if you're worried about super intelligent beings, you're not thinking about beings that are exactly like humans in all cognitive respects, with all the limitations, as well as whatever it is that they're seeking to emulate. So this is kind of unsurprising because humans are sort of unique among species. We are the only ones to have produced, science, vast edifices of knowledge, all of these, plethora of languages, different cultures, different cultural forms, and so forth. And it seems like this is whatever capacity is that underlies this ability of humans is kind of the target of the production of AGI. And of course, the benefits are indexed to this kind of thing, right? So for example, if we are thinking an AGI is going to advance science, solve world problems, find a cure for cancer and so forth. The AGI has to be able to represent scientific hypotheses, has to be able to learn from evidence in the way that humans do, maybe needs to know something about how humans act, so needs to have some kind of human theory of mind about the way humans behave. For example, if you're going to solve the problem of climate change, you have to understand how to affect or influence human behavior. And also with regard to the risks of harm, it seems like people who worry about AGI taking over or rendering us extinct, it's because the worry is that these systems will, as it were, occupy our niche, right? That they will be as intelligent as we are in relevant respects, if not more so, and therefore outcompete us. Of course, there are risks that we could be rendered extinct by totally unintelligent systems like deadly viruses, but that's not the kind of concern that's at issue here. Okay, so the question is, what is it that makes human intelligence distinctive in the relevant respects? And the answer, I think, comes with the term generality, like artificial general intelligence. In fact, historically, that term doesn't pick out exactly what we want it to pick out, but I do think it's an important indicator of what it is that we're interested in. We're interested in the generality of human intelligence. But the term general, just like the term AGI, has lots of different meanings. There's very different ways in which that is understood, also in the literature on AGI. So I'm not going to attempt a survey, I'm just going to discuss three. So the first is scope, flexibility, and what I'm calling generalization. And I'm going to explain what these terms mean presently. Okay, so first of all, scope. What is scope? So scope is basically the capacity to do many different kinds of things, right? Humans can ride bicycles, bake cakes, do math, write poetry, et cetera, et cetera. We can do many different things, and scope just refers to this kind of capacity to do a variety of different things, and also very different kinds of things, right? Okay, so for example, Morris and colleagues argue that AGI comes in levels reflecting the range of tasks an AI system can perform, right? And it's also linked to the AI system's performance on each task. So, for example, they say that if an AI system performs at the 50th percentile as indexed to human performance on a particular task, then that system is competent in that task, and then the ability can go up. But scope really has to do with the range of different tasks that the AI achieves a certain level of competence in. But it seems to me that scope does not capture what we care about in AGI. And the reason is, basically, you can have a system that does a lot of different things without being intelligent. So once upon a time, telephones could just do one thing, but now they can do many different things, and we just don't think that that makes them intelligent, right? And the reason is, I think, because, a bunch of different apps, it's just a fusion of different, very narrow capacities, even if each one was an AI, right? The fact that each one does something narrow, a fusion of narrow capacities to do different things is still not something that exhibits general intelligence. And one of the reasons is that scope doesn't really capture the ability to generalize from one situation to another situation. The apps on the phone are just are kind of encapsulated from one another. It doesn't go, the ability that it exhibits in one app doesn't translate to another app. And also, even there's no learning going on, right? There's no generalization from one situation to another situation within context. So one reason why we might care about generalization is that, in examples like self-driving cars, we want them to be able to perform as well in the real world as they do in the ideal situations in which they're trained. So we want generalization. We want the system to be able to generalize from one set of situations to another, and scope doesn't really capture that. Okay, so what about flexibility? Flexibility goes a little bit deeper than scope. and claims that the scope of things that humans can do, all of these different capacities that we have to do all these different things, is underwritten by a certain set of domain general capacities, such as reasoning, planning, problem solving, abstract thinking, comprehending complex ideas, one-shot learning, and learning from experience. This list is, there's disagreement about exactly what goes on this list, but many of these things are very commonly cited as among the domain general capacities that are distinctively human. So for example, Legg and Hutter put forward an account of AGI in terms of flexibility. They define flexibility as the ability to achieve goals in a wide range of environments. And so their account also comes in degrees, right? There's going to be a degree of flexibility that reflects how many different environments a system can achieve goals in. And the domain general skills are thought to be implicit in this definition. This is what they argue. They basically think that a system couldn't achieve a large number of different goals in different environments if it didn't have these domain general skills. But it seems to me that flexibility still doesn't capture generalization, which is something that we care about. So again, think of the iPhone, which is a fusion of different narrow systems, right? You can kind of imagine a fusion of systems, even just like putting together different types of goal-directed behavior that is suitable to different environments. So you might think a plant is capable of goal-directed behavior when it turns towards the sun. And it does so without reasoning or having any of the domain general capacities that seem to be distinctive of humans. But you could just fuse a bunch of those capacities together in a system, right? You could have a system that has all these modules that's capable of doing a variety of different things without having any kind of domain general capacity underlying all of those things, or indeed any one of them. Sorry. Moreover, non-human animals can also do many of the things on the list of domain general capacities, right? So if we were looking at something, we're looking for something distinctively human, there's a sense in which we shouldn't be just focusing on these capacities in some sense, right? So people have argued that animals are capable of reasoning, planning, problem solving, learning from experience. In fact, some people claim that animals are capable of pretty abstract conceptual grasp. I'm not sure what I think about that. I'm not sure I agree with that, but certainly there's some evidence that that in some sense of reasoning and in some sense of planning and so forth, non-human animals are capable of doing that. However, there's one caveat, which is that the evidence suggests that they do so in a very different way, right? So if we think about planning, for example, bonobos are capable of what looks like planning, but the best explanation of the way in which they plan is very different from the way in which humans, at least under some occasions, plan, right? So animals are capable of these kinds of associative, they engage in kind of associative learning and are capable of acquiring these kind of non-conceptual representations that associate behaviors with certain kinds of stimuli. And you can model the way in which they plan by looking at, by seeing it as a chaining or a linking of a series of these kind of associative representations. In contrast, when we think humans, when we plan, maybe what we do is at least in some cases, when we're explicitly planning, we might consider a space of possible actions we could perform. We consider the possible states of the world. We might consider, right, what the outcomes of particular actions would be given the different states of the world. And then we choose the actions based on our assessment of which one is likely to produce the best outcome given what we want. And that kind of planning is something that we don't see in animals. And I think one important aspect of what it is that goes on when we plan is that we are representing possibilities. We're representing possible situations, and there's nothing in the animal's behavior that suggests that that is the way that they're planning. Okay. So Generalization has already come up a couple of times in connection with scope and flexibility. It seems to be an important aspect of human level intelligence that we want to capture in AGI. So what is generalization? So I've just glossed it. Up to now is the capacity to generalize from one situation to another. And I want to note at the beginning that just as with planning and reasoning and so forth, generalization in this broad sense is not distinctively human. So, for example, the shape of a raptor can look different from different angles on different occasions, right? So a dormouse might be able to have, you know, a set of different experiences of a certain kind of raptors and be able to generalize on the basis of that experience to respond appropriately in new cases, right? So there's certainly an ability to generalize from limited experience to novel cases, even in animal cognition. Still, I want to argue that generalization of this kind is limited in certain distinctive respects. So the stimuli share certain properties that become associated in a kind of cluster. You can think about it as a kind of category. There's a bunch of properties that are associated together and that are then associated with a certain kind of behavior. So in the case of the dormouse is going to flee when it sees a shape and hears sounds, and you know there's a cluster of different experiences that it has at the same time. So if a new stimulus is going to instantiate enough of those properties in the cluster, then the behavioral routine is going to be initiated. But we don't need to postulate any kind of conceptual representation, right? This should be raptors rather than hawks. There's no capacity to represent raptors in the distant past or the distant future, or even merely possible raptors, right? So if you have the concept of a raptor, you can imagine, you know, a raptor that's minute, right? You know, microscopic in size, or a very, very large raptor or something like that, right? You can think about raptors in the distant past or the distant future, but there's no need to ascribe such a capacity to just explain the dormouse's ability to generalize from experience. Okay, sorry. So what is it that we care about in human level intelligence? Well, I want to say that there's two kinds of generalization that are distinctively human. I mean, maybe you can see some rudimentary versions of this in non-human animals, but we do this to a very extreme degree. One is the capacity for abstraction, and the other is recursion, so understanding recursive rules. Abstraction just means basically the capacity to acquire concepts that have an extension, they're sort of extended spatiotemporally and modally, right? We can think about, so in the case of the raptors, we can think about merely possible raptors. In fact, I mean, though this is a little bit more contentious, we can think about impossible things, not just possible things, but certainly abstraction allows us to think about possibilities. And in the example of planning that I gave, right, an important part of planning was what it involves representing possibilities. And so abstraction is a very important part of that, the ability to think about possibility. Recursion is also very important because it seems to be a crucial part of language. I'm going to say something more about this later, but recursive rules are basically rules that reapply to themselves, so the output of the rule can be input again. And this allows us to sort of generate infinitudes. For example, in the case of language, we can generate an infinite number of meaningful sentences based on finite resources. So this is really powerful, right? Abstraction and recursion are both really powerful because they put us in touch with possibility and they put us in touch with infinitude in a certain way. And I think these are capacities that are, at least to the degree that they're represented in humans, quite distinctive. So the example I want to give is the example of the learning of number words and number concepts, the concept of number and the concepts associated with that. At a certain age, children learn to count. And when they do, right, so once they are able to count, say, not just to 10, but to 17 or 25, or, you know, they start to get this idea that you can just keep going. What's happening here is they're grasping a concept with an infinite extension based on some finite experience. So the concept of number, once children start to grasp this, they grasp the concept of number along with the successor function, which just says that the successor of any given number is that number plus 1. So Susan Carey describes this process in a very illuminating way. So, I mean, just very briefly, children kind of start understanding the concept 1, they become 1 knowers first, and then they become 2 knowers, and then they become 3 knowers. But at each of these stages, they're sort of limited to these, you know, the number of concepts that they can grasp. And then at a certain point, they seem to grasp the successor function, and then they can just go on, right? They can count. But prior to this, so non-human animals and pre-linguistic infants are capable of assessing magnitudes in various different ways. So it's not the case that animals are incapable of assessing magnitudes. So here's one way that they do it. They use analog magnitude models, which involve a kind of linear neural representation that corresponds to the approximate size of a set. Right, so you can see here, no, that's not working. Okay, so one, you know, so the length of the line that's associated with 1 and 2 is reflective of the approximate size. And one feature of these analog magnitude models is that they satisfy Weber's law, that the discriminability of 2 values is going to be a function of their ratio. So for example, it's easier to tell the difference between 1 and 2 than it is to tell the difference between 7 and 8 in this diagram. And there comes a point where the differences, so, you know, between 57 and 58 is going to be extremely difficult. You won't be able to just see the magnitude. You have to be able to count in order to tell the difference. The other kind of model is the so-called parallel individuation model. So pre-linguistic children and non-human animals can represent numbers of objects individually like this. So if you have, these are little diamonds in this case. So you have these little diamonds, you perceive them, and in the parallel individuation models, you have separate representations for each of those items, and you track them visually and store those kind of representations temporarily in working memory. And that's the way, that's one way in which we can represent magnitudes. But there's severe limitations of this representation because we can only keep track of so many objects in working memory, and so we can't get above a certain number. So analog magnitude representations are not abstract concepts of number, right? In the case of the abstract concept, if you can think 7 is greater than 1, and you think 8, you can think 8 is greater than 2, you can also think 8 is greater than 7, right? There's nothing that's preventing you. That's an exact concept, and you can, once you've grasped these concepts of number, you can compare them in any number of ways. But with analog magnitude representations, you can't do that, right? You might be able to represent, you know, some set of 7 objects is greater than 1, a set of 1 object. And you might also be able to recognize 8 objects as greater than 2, but you still can't represent 8 objects as greater than 7. So it satisfies, it doesn't correspond to the abstract concept. And parallel individuation models are not abstract concepts of number either. So in these models, there's no representation that corresponds to number, but rather, if you recall in the diagram, each individual is tracked separately. So there's no representation that corresponds to the number of objects in the set. Okay, so why care about these things, abstraction and recursion? So the successor function is a recursive rule. That's why recursion is relevant in that case as well. So why care about these things? So abstract concepts, as I've already said, just noted, they represent possibilities. They allow us to represent possibilities. And the representation of possibilities seems to be necessary for distinctively human planning. It's also, I think, necessary for distinctively human learning from experience. So this is also one of these things that's characterized as distinctively human. But of course, all animals learn from experience. Well, I don't know, maybe some don't, but all, like many, if you've seen a dog learn to sit on command, then you know that an animal can learn from experience. But we seem to think that animals and humans learn from experience in different ways. Humans can also learn from experience in the way that animals do by a kind of habituation or associative learning. But one of the things that's distinctive about human learning from experience is that we're able to formulate general hypotheses. We're able to represent a space of possible hypotheses and able to allow evidence to come in to adjust our confidence in various such hypotheses. And this is crucial for scientific investigation. So if we were kind of concerned about, if we were interested in an AGI that is able to do that, that's able to do science, I think that we care about an AGI that's capable of abstraction and recursion. Abstraction and recursion are also necessary for understanding natural languages, such as English or Hindi, right? Chomsky argues, for example, that recursion is an essential feature of language that's maybe been challenged, but at any rate, there are, it seems to me that, well, it seems to everyone that many languages are recursive, right? That languages like Hindi and English contain recursive syntax and semantic rules. So one important aspect of AGI, for example, when we evaluate ChatGPT, so Bubek's argument in part relies on the claim that ChatGPT can genuinely understand language, but that requires both abstraction and understanding the concepts, understanding the abstract meanings of terms, and it requires recursion, the ability to understand recursive rules of language, both syntactic and semantic. Of course, we also care about generalization, going back to the self-driving car. So on the basis, generalization on the basis of non-conceptual representations, as I've argued, is limited, right? So generalization in the case of the dormouse's representation of the raptors is limited. And we might want generalization, a capacity for generalization that is not so limited, that is more like the kind of generalization that we are capable of. So for example, we might want a self-driving car to be able to grasp certain relevant concepts, like the concept of a pedestrian, right? And extend those to novel cases, not just kind of clusters of properties that it happens to experience in the learning environment. So for example, if the cars only encountered humans of within a certain height range, we want it to be able to generalize to humans maybe way outside of that height range, or viewed from very different angles. And one of the reasons why we might want to do that, why we might want a system that can grasp concepts, is because we can't specify in advance what all of those situations are going to look like, right? All of the varied situations that the car might find itself in the real world in advance. So grasping the concepts, the relevant concepts in the right way is going to be the thing that we care about. Okay. So let me turn to benchmarking. Do I have like 10 more minutes or something like that? Because we started a little late. Yeah. Okay. So finally, the topic of the workshop, I come to this. So benchmarking. I've already mentioned some of, I'm basically going to argue against shallow methods of benchmarking. I have a few things to say about what we might hope for from deep methods, but I'm basically going to argue against shallow methods, but I'm not going to use the arguments that are familiar, the kind of Ned Block, blockhead argument, nor the Searle's Chinese room argument, both of which are well known in AGI. I'm going to use another old argument, which is the sort of Kripke's argument based on Wittgenstein's rule-following considerations, right? So I'm going to argue that this applies in this case, and this is one of these things that I find, just as a meta comment to the philosophers in the room, this is one of the things that I find really interesting about working on AI, is that some of these old philosophical questions apply in these new cases, and it turns out that the considerations are slightly different, and therefore this exercise is not just rehashing a bunch of old arguments, but it looks like it makes us rethink how they work in this case. So, oh yeah, I should just say Kripke plus Wittgenstein is Kripkenstein. This is because Kripke, when he gives his account of Wittgenstein's rule-following considerations, doesn't actually endorse them, but he puts them forward as the arguments in Wittgenstein as they struck him, and so he's come. This kind of mishmash of Kripke and Wittgenstein has come to be known as Kripkenstein. And there's the references. Okay, so I'm not talking about any actual systems here. Just imagine the system Artie. This is Artie. And we're going to imagine Artie meeting Kripkenstein. So we teach Artie to count up to 1,000. Artie performs well repeatedly when tested. We conclude that Artie has grasped the concept number and the successor function. But now a skeptic comes along and advances the following hypothesis. Wait for it. Artie does not grasp the concept number or the successor function. What she's grasped is the concept schnumber and the successor function, which is defined as basically equivalent to the successor function up to the number 1,000, but then deviates from the successor function above 1,000. So you can't, if you're going to count, if you've got the concept schnumber and you're counting, you'll count up to 1,000 by ones, and then you'll count by twos above 1,000. Okay. And then the skeptic points out all the facts about Artie's performance are consistent with the hypothesis that she's grasped the concept of schnumber rather than the concept of number. And then the skeptic goes on to point out that, look, this choice of breakpoint at 1,000 is arbitrary and the natural numbers are infinite. So if you tried to come back and say, look, we'll just get Artie to perform a few more tests, right? We can just ask Artie to count above 1,000 and see how she does. The skeptic is going to say, well, I'll just invent a new hypothesis that deviates from the successor function at some other point. And so there will always be a deviant rule that's compatible with Artie's finite behavior, whatever it is. So however much we observe, there's going to be another rule in the offing that's consistent with all of that behavior. Okay, so one kind of reply that you might immediately want to make is the sort of good bedfellows reply. Look, this is just the problem of underdetermination of theory by data that affects all scientific theories, physics, chemistry, biology, and so forth. We have the same problem there, that the totality of the data is going to be compatible with multiple inconsistent theories. So maybe we can just appeal to some simplicity considerations to break the tie, right? So in the sciences, for example, people will appeal to other sorts of theoretical virtues besides explanatory, or besides experimental, or conformity to the data, right? What am I looking for? Empirical success, right? So beyond empirical success, there are other sorts of virtues that you might look for in a scientific theory. You might care about its explanatoriness. You might care about its fruitfulness or its scope or its simplicity. And one thought is, look, we can appeal to simplicity considerations to break the tie. The concept number is simpler than the concept schnumber. And so we should attribute that concept to Artie. However, it seems to me that for various reasons, the simplicity considerations break the tie in favor of the skeptical hypothesis or some other skeptical hypotheses, right? So to begin with, there's no reason to think that an artificial system should latch onto the concepts that seem natural or seem simplest to us. Sorry. And in fact, there's some reason to think that specifically large language models, these really large models with many parameters, there's something just surprising on the basis of classical statistics. Classical statistics predicts that a model with so many parameters will tend to overfit the data and therefore not generalize in the way that we expect it to do. And it's kind of surprising and difficult to explain why it is that these very large models can do this. So to that extent, you might think, well, given what we know about the way these systems are designed, simplicity considerations don't seem to break the tie in favor of the hypothesis that these systems are able to generalize in the way that we are with the concepts that we have. And also, it seems to me the skeptic can advance two further skeptical hypotheses. One is the zombie hypothesis that Arti has grasped no concepts, right? So the states of Arti's system they carry information, but they're not represented to Arti at all. And so we can think about cases like, for example, the way in which your brain represents states of your body, physical states of your body to which you have no cognitive access, right? Your brain is constantly monitoring various states of your physical body that you don't pay attention to, right? So there's representation going on in the brain. It's carrying information in a certain sense, but it's not anything that's accessible to you that you have any knowledge of. And so we might think of the zombie hypothesis as put forward in that way. Or you might think that all Arti has is certain non-conceptual representations, not conceptual ones. And both of those hypotheses seem to be at least ontologically simpler than the hypothesis that Arti has grasped concepts, right? Because the first one doesn't ascribe any unobservable representations at all. And the second one ascribes much less sophisticated capacities than the one that we might naturally adopt. Okay, then there's the tu quoque reply. Look, the rule following considerations imply that we don't know that humans grasp the concept number either. I mean, after all, the metaphysical justification. So in Kripke's own elaboration of Wittgenstein's rule following considerations, he asks the question that I have asked, which is how do we know, or how could we just be justified in believing that a system such as Arti has grasped the concept of number? That's an epistemological question. But Kripke also asks this metaphysical question: what makes it the case that a system grasps one concept or the other? And he argues that, thinking about humans in this case, not about artificial systems, that there are just no facts of the matter to be known, right? There are no facts about concept grasp, no facts about understanding of meaning to be known at all. And so we, in the human case, since there are no facts of the relevant kind to be known, we can't have any knowledge of them. But as even Kripke notes, and I think many commentators have pointed out, this has a kind of air of paradox about it. I have a lot to say about this case, so I'm not going to bore you with all the details, but I think one way to get your head around what's sort of weirdly paradoxical about claiming that we don't grasp abstract concepts, but there's no facts of this kind to be known, is that, look, when I just spelled out the kind of skeptical problem, you guys, I take it, grasp the concepts of number and the invented concept of schnumber. You grasp general claims about what it is to understand those sorts of things. And if you didn't grasp abstract concepts, you wouldn't have understood the arguments that led up to the nihilistic conclusion that the skeptic wants to draw. So I'm just going to kind of set aside that kind of response and say, look, there are some facts of this kind. We do grasp abstract concepts. We have very good reason to think so. So another kind of justification for the tu quoque response is the kind of instrumentalist justification. This is kind of due to Daniel Dennett. So if the intentional stance works best with respect to humans, for example, but also with respect to artificial systems, then we're justified in using it. Questions of realism and underdetermination aside, right? We just ignore those questions and just go with what works. But the problem is that this only justifies using the intentional stance in ordinary contexts, but not in contexts where we're actually probing the underlying capacities of a system. So even Dennett thinks that if we really want to understand these systems, we need to adopt the design stance, right? We need to be able to look under the hood. Okay. So Dennett thinks that, sure, if you're just like, if you just have ChatGPT on your phone and you're kind of playing around with it, sure, it's fine to use the intentional stance. Or if you're playing chess, he's talking about, old school chess computers in his paper on intentional systems. He says, like if you're playing chess against one of these systems, it's perfectly natural and it's perfectly fine to use the intentional stance to imagine it thinking about possible moves and so on. But when we really want to understand how this system works, we need to adopt what Dennett calls the design stance, which is to say that we need to understand its internal structure and function. Okay, I think that I'm going to leave it there because this is the end of the kind of argument against the shallow accounts. I had another section where I was going to say why I thought looking under the hood might help or what it might get us. But maybe people will be interested in asking about that in the question period. Thank you very much for listening.